Recall from our study of the frequency response in Chapter 14 that time delays have a strong influence on stability of feedback control loops. The time delay by itself causes the phase angle to cross minus 180 degrees at some finite value of input frequency, omega. Therefore, the controller gain has an upper bound under which it must remain in order for the feedback control loop to be stable. Consider an SOPTD process. If this process did not have the time delay, then we could tune a PI controller with any gain we choose, and it should remain stable, because the second order process without a time delay always has a phase angle above minus 180 degrees. In this case, we might tune the PI controller with a gain of around 3 and a reset time of about 6.5. However, when the time delay is present, the PI controller must be tuned more conservatively to obtain approximately the same value of the overshoot. In this case, the gain must be reduced by more than half to 1.23, and the reset time slightly increased. Although these two responses have similar overshoots, they have very different settling times. Adding just a 2-minute time delay to the process leads to about a 15-minute difference in the settling time following set point changes for this feedback control loop. You may recall that the direct synthesis method for a process containing a time delay gives an ideal controller that has the time delay appear in the denominator. Now, when we used the direct synthesis method, we said that we didn't have a way of tuning a controller with a time delay in the denominator. So instead, we introduced the internal model control method. But although this is not a standard PID controller, if the model is perfect, we can still tune a controller this way, and it's called a Smith predictor. We obtain the time delay in the denominator by nesting an additional loop inside the controller, and that additional loop contains a time delay. Here, the function g tilde star represents the model for g without the time delay. So g tilde is a model that is approximately equal to the transfer function g. That model is g tilde star multiplied by a model for the time delay that's contained within g. We'll call e to the minus theta tilde s, where theta tilde is an approximation for the time delay theta contained in g. This signal now that is fed back inside the controller is the difference between the model of the process without the time delay and the model of the process with the time delay. That essentially adds back the effect of the time delay to the error signal. So the error signal going to the controller is actually a prediction of what the error will be in the future after the time delay. A feedback control loop tuned with an internal time delay like this is called a Smith predictor. Let's compare a PI controller tuned for this process containing the time delay to a Smith predictor. Now, when the process contains the time delay, if we don't use the Smith predictor, we found that we had to detune the controller. That is, we had to make it much more conservative in order to obtain a similar overshoot. The curves shown here on the right compare the process without the time delay, tuned using our original settings, to the process containing the time delay, but tuned using a Smith predictor. When the Smith predictor is used, we can use our original settings for Kc and tau I. And now the response to set point changes is very similar to the response we would have gotten if the process did not contain the time delay, only it is delayed in time by an amount equal to the time delay. That is, it's delayed by the 2 time units. Now we'll call G' the Smith predictor controller tuned according to the direct synthesis method, which is shown here. If our model for the process is perfect, that is, if g tilde is exactly equal to g, then g tilde star e to the minus theta tilde s is exactly equal to g star e to the minus theta s. If our process g is an FOPTD model, then g star it's the same as g without the time delay. Substituting g in for g tilde, we find that the time delay in g' cancels with the time delay in g, and therefore this term is just 1 over g star. Now we can simplify g' and find that GC appears in the numerator and the denominator. This GC is a PI controller. When we combine GC with the additional inner feedback loop containing the time delay, we obtain what we call the Smith predictor, the block diagram of which is shown here. This entire thing outlined in the blue broken line is the controller using the Smith predictor scheme, which gives an output P to the valve when it's fed an error signal E. Substituting our Smith predictor into the servo transfer function, we find that the output in response to set point changes will be first order with our desired closed loop time constant tau c, but simply delayed in time by e to the minus theta s, where theta is the time delay in the process and the time delay used in our model in the Smith predictor. The servo and regulator transfer functions for a feedback control loop tuned using a Smith predictor are shown here. Usually the Smith predictor does a reasonably good job with disturbances as well as set point changes. When tuning a Smith predictor, we have to have a pretty good model for our process, including a good estimate for the value of the time delay. The Smith predictor has been around for more than 50 years, so there is a lot of literature on tuning procedures for Smith predictors. Generally, the Smith predictor is tuned by first finding a model for the process, including a model for the time delay, theta tilde. Then, assuming that the process does not contain the time delay, that is, setting theta to 0, and tuning using one of the methods from Chapter 12, such as the IMC or direct synthesis method. Those settings are then applied in GC. Then the theta tilde from our model for the process is implemented in the time delay compensation. So in general, the Smith predictor can be tuned assuming that the process has no time delay and then implementing the time delay compensation.